Hello and welcome to this lesson on Kernel Loadable Modules as part of the class on Linux device drivers. In this module, we will first of all consider just what is a kernel loadable module and what's it good for. We'll look at some of the tools that Linux provides for managing modules. We'll see that modules are kernel version specific. And finally, we'll look at the interesting relationship of modules to the GPL. For the remainder of this class, I recommend that you log into your Linux system as root. Yes, I know good practice says you shouldn't log in as root unless you absolutely have to and know precisely what you're doing. But just about everything we do in this class requires root privilege, so log in as root and just be careful. Fundamentally, loadable kernel modules are a way to extend the functionality of the kernel at runtime without having to rebuild it. They can be loaded and unloaded while the system is running. Modules execute in kernel space at privilege level 0, so a buggy module has the potential to bring down the system. Kernel modules are particularly useful for device drivers. Think about it. Linux supports literally thousands of devices. It would be virtually impossible, not to mention silly, to try to build that much driver functionality into the kernel itself. So Linux distributions distribute the vast majority of drivers as modules. At boot time, the kernel determines which drivers it needs and loads those modules. Only the drivers needed to boot the system are built into the kernel image. File system drivers are another good use for modules. A module is installed into the kernel by executing the insmod command. When that functionality is no longer needed, the module can be removed and its memory space reclaimed by executing rmmod. Note that insmod allows parameters to be passed to the module. You must be root or superuser to invoke these commands. A couple of slides back, I suggested you log into your system as root. There are a couple of alternatives to that. You can easily become root with the command su. It will ask for the root password, and now you're the root. If you become root with su, you may have to preface the insmod and rmmod commands with /sbin/ because /sbin is not normally in a regular user's path. Then there's another command called sudo, that's spelled sudo, that lets you become root with your own password if you've been authorized by the system administrator. The basic requirement for a kernel module, other than being thoroughly debugged, is that it include at least two functions. The module initialization function is called as part of insmod to initialize the module. And the module exit function is called, not surprisingly, as part of rmmod to clean up when the module is removed. Here's a typical module install command that also illustrates how parameters are passed to a module. Parameters can be integers of any length or strings. Here's a module initialization function. Its fundamental role is to make the module's presence known to the kernel and inform the kernel what it's capable of doing. It does this by calling one or more kernel services that register various capabilities, such as device drivers, /proc files, and so on. In effect, what the module is telling the kernel is, hey, here I am, and this is what I can do. In the case of a device driver module, the initialization function may also initialize the hardware. Note the macro module init, which identifies the function to be used for module initialization. This slide illustrates graphically how a module becomes part of the kernel. The insmod command calls init module. The primary role of a init module is to register the module with the kernel by filling in some kind of capabilities data structure with pointers to functions within the module. For the purposes of this class, the capability structure is the file operations structure that we'll encounter in the next lesson. The functions in the module are able to invoke services of the kernel to carry out their mission. Finally, the system user may decide that the services of the module are no longer necessary and invoke rmmod to remove it. This calls the module's cleanup function to remove the function table pointer from the capabilities table and return any resources that may have been allocated to the module, such as dynamic memory. Now, here's a question for you to contemplate. The module is an independently loaded program from the kernel itself. In fact, it's a relocatable object file containing unresolved external symbols, much like the components of a user space application. These unresolved externals are the kernel services. So, how do these external symbols get resolved? Well, it turns out that when the kernel is booted, the kernel symbol table gets loaded along with it. So insmod resolves the module's external symbols against the kernel symbol table. Furthermore, any exported symbols declared in the module get added to the kernel symbol table so that subsequently loaded modules can make use of the facilities of this module. Linux distributions include a set of utilities for managing kernel modules. lsmod lists the modules currently loaded in the system. We'll take a look at it in the upcoming demo. And actually, we've already looked at insmod and rmmod. Insmod may fail because the module it's trying to load is dependent on another module that hasn't been loaded. The modprobe utility also installs a module, but it works out all the dependencies first and loads the modules in the correct order. The next point we should note is that a compiled module is bound to a specific version of the kernel. If you try to insmod a module into a kernel other than the version it was built for, it fails. That's because modules make use of services provided by the kernel, and the kernel APIs change between versions. So if you build a module against one kernel's API definitions and then load it into another kernel version, it may fail because one or more APIs changed. As a consequence, a module is always built from within the source tree of the kernel version for which it's intended. There's a link under the appropriate subfolder of /lib/modules that points to the kernel source tree. It doesn't have to be the complete source tree, by the way, just those files needed to resolve various kernel dependencies, such as header and configuration files primarily. When you install a Linux distribution, you'll usually get such an abbreviated source tree for the distribution's kernel so you can build modules against it. What usually happens then is that the makefile in the directory with your module source code changes directories to the kernel source tree and invokes the makefile there. We'll look at an example of how that works in the upcoming demo. When I say that kernel APIs change, that includes the device driver APIs that we'll discuss in this class. The consequence of this is that some of the examples may not build under an earlier version of the kernel and may not build at some point in the future. The examples were built and tested under the 3.10 kernel that ships with CentOS 7. I should point out that insmod has a force option, -F, that will load a module even if the signature doesn't match the running kernel. A lot of times you can get away with that, but don't count on it. There's an interesting licensing issue surrounding loadable modules. Remember that the Linux kernel is released under the GNU General Public License, the GPL. A key provision of the GPL is that any code that makes use of or is in any way built upon code licensed under the GPL is termed a derivative work and is itself subject to the terms of the GPL. Specifically, the source code must be made available. Pretty much everyone agrees that applications running in user space and only using the published services of the kernel are not derivative works as defined by the GPL and can be maintained as proprietary. On the other hand, anything built into the kernel itself is clearly a derivative work and must be released in source code form. Modules occupy a middle ground. Even though modules make use of kernel code, they are by mutual agreement allowed to remain proprietary, although not everyone agrees with this position. There was a move a couple of years ago to simply prevent non-open source modules from loading. Linus said absolutely not. Doing that would kill the commercial viability of Linux. Hardware vendors have a legitimate interest in maintaining their device drivers as proprietary. If they had to release their driver source code, it would reveal the inner workings of their proprietary hardware. If forced to release their source code, they may simply choose not to support Linux. Now then, many kernel configuration options, including most device drivers, offer the choice of building the feature as a module or building it into the kernel image. If the feature is built into the kernel, it must be GPL'd. So if you want to maintain your driver as proprietary, release it only as a binary module and don't offer the option to build it into the kernel. If you think about it, this is semantic hair splitting, but it does serve a practical purpose. You might be tempted to say, well, heck, I'll just put the module license macro in there and keep the kernel happy, but not release the source code anyway. Who's going to know? Trust me, someone will catch on. The open source police are out there, and the community takes the GPL very seriously. Companies have been taken to court and enjoined for violating the terms of the GPL. Don't do it. Time for a quick review before we sign off. What we learned first and foremost in this lesson is that loadable kernel modules are a way to dynamically extend the functionality of the Linux kernel at runtime without rebuilding the kernel. Every module must have at least two functions that link it to the base kernel. The initialization function serves to link the module into existing kernel functionality. The exit function reverses the actions of the initialization function to be sure that all resources are properly returned to the system. Modules are kernel version specific. This means they are built against a specific version of the Linux kernel. Attempting to load a module into a kernel version for which it was not built will fail. Modules can only be built from within a kernel source tree. Modules enjoy a special status with respect to the GPL. Even though they make use of GPL kernel code, they are allowed to remain proprietary. Well, that's it for this session. Thanks for joining me.